Hi there. This is a series of advanced mathematics video for data scientists. We will cover category, group representation, graph, and manifold. In this video, we will cover manifold theory. So what is a manifold? A manifold, we denoted by M, is a notion that generalizes the space. Here we consider a sphere. Suppose we take a patch from this sphere. We require that this patch be like Rn and look like Rn for some n. So this is a simple example of a manifold. Why we should learn it? In physics, we learn it for using it in like general relativity. In AI, we have data manifolds that tell us high-dimensional data often lives in a low-dimension manifold. And in robotic, we can use it for control of the robot. The points may lie in a submanifold. So let's go in the details of what a manifold is. A topological manifold is a Hausdorff and second countable that look like Rn at each point. And we have some maps that we call charts, like the patch that we saw on the first slide. So let's take our sphere again. Here we take a patch of our sphere. So this patch is denoted by U. And we have a function phi that can map it to the Rn. So it is like Rn at each point. So this map phi is called a chart and is a homeomorphism, which means continuous, bijective, and continuous inverse. So when we can do calculus on a manifold, when we have a smooth structure. So for a smooth structure, we have to have this compatibility condition. Let's see what this compatibility condition means. Suppose we take two patch, U and V. U is the red one and V is the blue patch. And the function phi and psi map these to Rn. So if we go through psi, then phi inverse, this should be infinitely differentiable. Next, you have the concept of tangent space at a point. This is a space of a certain class of curves, or we can see it through the algebraic lens also. So let's see what this tangent space means. Suppose we have a point and we have some curves going through it. So these curves at that point shape a plane. This plane is called tangent space, and this is the basis of this tangent space, as we know. Next, we have differential forms. Let's recall we had some vectors, and we can write it in a basis. We can define a dual space for this vector space, and we can define basis for this dual space also. So this is an example of a vector V written in its basis. We can define vectors to vectors and covectors to get something else. This something else is called forms. So we have, like in tangent space, we have these bases, and in the cotangent space, we have E superscript, and E subscript is for the tangent space. Also, we can define the metric. Metric is also a combination of forms. It is a tensor product of forms. Next, we have the concept of submanifold. We can have two kinds of submanifold, which means that we have a manifold that inherits the structure of the original manifold. So we have an immersion or an embedding. Next, we define the metric. So a smooth manifold with such a metric is called a Riemannian manifold. And we have the concept of geodesic also. So let's see what a geodesic is. This is the concept of the metric space. So this metric defines the length of a vector at each point. And we have the concept of geodesic, which means we can go through the shortest path, and this is called the geodesic. Like in a manifold, we can choose which path we take, and the geodesic is the shortest path that we can take. If we have a vector field on a manifold, this generates a flow, and we have something called Lie bracket, which is defined like in this bracket, and F is our vector field. We can measure this Lie bracket and see how this vector field commutes. So we have something, this is our vector field like on the sphere. If we go through this vector field, we feel the field differently.